find fuel, airstrips, maintenance crews, spare parts, navigational systems, and all the other paraphernalia that keeps it flying, and a 747 is just a large piece of scrap metal. A bird, an adaptable living system which can also fly, can live on berries, seeds, worms, insects, small rodents, fish, and bits of bread tossed to it by amused tourists. Its remarkably adaptable digestive system can convert all these and more into energy and essential raw materials for power and self-repair. It thrives in the complex and ever-changing natural world. But artificial systems are going to be different. How many people here have heard of the broadcast architecture? Hands. Broadcast architecture. A handful of people. Okay. A brief discussion of the broadcast architecture, which I see has to be taking place in 5 minutes. A brief discussion of the broadcast architecture is as follows. Living systems, cells, replicate by having DNA, a complete set of blueprints, on board. So the complete set of blueprints is copied. The cell makes 2 cells. The blueprints are transcribed into the new cells. In the broadcast architecture, instead of having the blueprints on board the device that replicates, you have the blueprints somewhere else in a central computer. The blueprints are broadcast to the devices. The devices are, as a consequence, simpler. They have fewer components. They don't have to have the storage of the entire complex blueprint structure. They can be more readily redirected to manufacture economically useful products and can replicate more rapidly because they're smaller and simpler. So the broadcast architecture appears to be advantageous. It is very much non-biological. If you adopt the broadcast architecture, then suddenly the concerns about devices running amok in nature go away. If you flush these devices down the toilet, they're cut off from their instruction stream. They cannot function. So that is one architecture, one approach, which is radically different from the biological approach and which illustrates that we can design systems that can be intrinsically safe. Well, I do not expect that everyone will immediately agree with the assessment that we can design intrinsically safe, self-replicating systems. The point is not to resolve the issue today, but that we as a society need a mechanism for resolving this and other complex issues. We can hardly decide on a wise course of action when there are still fundamental disagreements about the basic nature of the technology whose development we are trying to guide. We need a research community actively investigating the design of artificial, self-replicating manufacturing systems, such as assemblers, whose members can provide us with multiple perspectives and a wide range of views. Views developed over years and decades of careful investigation of such systems. And if 10 years from now we want a community of researchers who have spent a decade working on the design of such systems, we need to start today. Accidents are only one cause for concern. A greater cause for concern is deliberate abuse. New technologies are used to make new weapons. A fundamental question raised by new technologies is, does it favor defense or offense? Castles favored defense. They were harder to break down. They made it more difficult to attack. Nuclear weapons favored offense. They made it easier to attack and harder to prevent attack. Will nanotechnology favor offense or defense? This is a complex question, which I and others have considered for decades. To the best of my knowledge, there is as yet no clear answer. From a practical point of view, the answer to this question matters a great deal. If nanotechnology favors defense, then we should learn and understand how to make such defensive systems as rapidly as possible. If nanotechnology favors offense, then we need to know this unwelcome news as soon as possible so that we can start seriously investigating the issues surrounding arms control, proliferation, verification, and the like. What then should we do? Pursue an active research program coupled with informed public discussions to guide public policy towards the safest courses of action. And I think I've run out of time.
You have 1 minute.
1 minute. Well, in that case, let me expand upon this last point. There is an important area of research which needs to be pursued, but which is not being pursued today. That is the theoretical and computational investigation of artificial self-replicating manufacturing systems in general, and assemblers in particular. If we are to gain some collective insight into where technology might reasonably go over the course of the next 20 years, we must use theoretical and computational tools. Experimental research tells us what we can do today and suggests what we might be able to do in the next few years, but it cannot address the longer-term issues of where will we be going over the next few decades, what is permitted by physical law, what can we achieve within that framework. Thank you very much.